Hello there, chemistry student, chemistry lover. Here we are with another problem-solving session. And I was thinking about going with an actual exam question. This is something that I had on an exam 3 from a semester, a few years ago, I think at this point. And it has to do with kinetics and mechanisms. It's a little bit different from the other kinetics videos that I've made in the past. So let's take a look at what this is asking. So what this problem gives is a proposed mechanism for the decomposition of hydrogen peroxide. And it gives the mechanism, it gives the activation energies for each step. It's a 2-step mechanism. But it doesn't give the overall or net equation. This is one of the questions that it's asking for. And it's also asking which one is the rate determining step. So this is where we're going to look at the activation energies to answer that. And we'll also see, is there a catalyst? Another question about the catalyst being homogeneous or heterogeneous, and the overall rate law. There's another question that I'm going to ask of you, and that is about the intermediate. Is there an intermediate that exists? And if so, what is it? Okay, so let's dive in to this question and investigate how we're going to answer it. Okay. So, I don't know how my ink is going to do on this paper, because this is regular paper, so we're going to find out. It might act interesting. We'll see. Okay, so our overall reaction, if this is a mechanism, what needs to be true for any mechanism is that the steps always add up to give the overall, or in other words, the net equation. So one way we can do this is we can cancel out anything that appears on both sides. And we can either do that directly on the step as it's written here. This is an elementary step. This is an elementary step. And so if we want, we can cross them out. Or we can do it another way. We can add up everything that's on the reactant side and write that out. And I'm going to do that so that we can see really clearly what it is that appears on each side and what we can safely cross out. So I'm going to write out this H2O2, that's our hydrogen peroxide. I'm going to write out our plus iodide. Here, we're going to add in, because remember we're adding everything on the reactant side. I'm going to add this other H2O2. And I'm going to add in this IO minus here. Okay, so that's just everything I'm listing here is on this side. And now, let's write out everything that's on the product side. With H2O, we have this IO minus here and here. I'll write out all these that are in step 2. adding them all up. There's our H2O. There's an oxygen, O2. And there's an iodide ion, I minus. Okay, so now let's assess what is on both sides. So just like in a mathematical equation, if you had plus x on one side and plus x on the other side, you could subtract x from both sides and remove them. We can do the same in chemical equations, and we're going to do that with the iodide here because it appears on both sides. So the net equation, we won't see the iodide. What else appears on both sides? Yeah, it's this IO minus, isn't it? So we can cross that out on both sides. Alright, then we take a look and we see that everything else is unique on the reactant side and on the product side. And in the case here, we have two H2O2s, so we can combine those together. Call it 2H2O2. That's everything on the reactant side. And then, in terms of the product side, we have two water molecules and one oxygen. Okay, so there is our net equation, or in other words, the overall reaction. Okay, now, which one of these is the rate determining step? Okay, so it is now referring back to the mechanism, step 1 and step 2. And the rate determining step, that is the very fastest this reaction can go. So in other words, this is the slow step. Okay, it's going to be the slowest step of the two. So I'm just going to write that as a reminder. This is the slow step. And we look here, and we've been given some information. One of these has an activation energy of 56 kilojoules per mole. The other one is given an activation energy of 43 kilojoules per mole. Which one is bigger? Okay, step 1. And what does that mean? That the activation energy is larger. And what is the activation energy anyway? That's a good question. So I'm going to draw over here to the side an energy diagram. And this is often called a reaction coordinate diagram, where we are following the overall energy of this chemical reaction. And so I'm just going to say this is energy. We're not going to get really specific with enthalpy or Gibbs free energy. We're just looking at this from a very qualitative point of view. But we are going to look at these energies as a guide. And what this means is that overall, if we look at our reactants, there's an activation energy for our first step. And that means that the energy goes up, and any molecules that are reacting need to make it over this barrier. And this difference between the energy of the reactants, so this would be our two H2O2 molecules here, if they're going to react, they need enough energy to make it over this barrier. there is a second step here, and this has an activation energy that's a little bit less than that. So what it means is that there's another barrier here that is not as large as this one. So see this from here to here? If this equals from there to there 56 kilojoules per mole, from here to here, from the start of this minimum up to here, this is less. This is our 43 kilojoules per mole. Now, it just so happens this reaction is exothermic, so we're going to have our products down here. That's where our water and our oxygen are. But what it means is that step one is a larger barrier, a larger energy barrier. And so this will be the slow step. When you have a larger activation energy, it will happen slower. The molecules don't need as much energy. So not only will this be the slow step, but we can add in that this has the larger, and we can in fact say it's the largest activation energy of however many steps you have. And in this case, we have 2 elementary steps in this mechanism. So, identify the rate determining step would be step number 1. Okay. Next, identify the catalyst. Okay. This has a catalyst. How do we know? And what catalyst is it? And what is a catalyst? Well, a catalyst is something that you add in. The experimentalist adds the catalyst. It is transformed during the course of the reaction into something else. So you could look at it from a point of view that the catalyst disappears, but then it is regenerated in a later step. So in this case, iodide fits the bill for a catalyst. It appears as a reactant, something that was added in. So here it's in a reactant, as a reactant first. That's the first time it appears, is as a reactant. It is then transformed, meaning that here in the products we don't see iodide anymore, but instead that iodide had an oxygen that bonded to it. The origin of that oxygen was from the hydrogen peroxide. Now here's the oxygen bonded to the iodide, and it is a new species. But we can see here in step 2 that there was another elementary step where iodide was regenerated. So that is how we identify a catalyst in terms of where it is if we have a mechanism. It appears first as a reactant, and then in a later step as a product. Okay. So that's how we identified it. Now, what was its role? Well, catalysts do what? They help chemical reactions go faster, right? In this case, the overall reaction, the decomposition of aqueous hydrogen peroxide. Here's the net reaction. hydrogen peroxide decomposes into water and oxygen. This happens very slowly in one step when there's no catalyst. Very slowly, and when I say very slowly, I'm talking years. Half-life is very long. However, if you add in some iodide, like so many people do in elephant's toothpaste, I think a lot of you may have seen a lot of super cool videos of elephant toothpaste. Are really fun. And the catalyst is iodide. And it bubbles because with elephant's toothpaste, usually people put in dish soap and oxygen is created, making bubbles. So it makes the dish soap bubble up. And this is essentially one of the main things that happens with elephant's toothpaste. You also may have seen that it gets all steamy and hot, and that's because it is exothermic. Okay. Let's do something else here. I didn't put it on this exam. I don't know why. I usually love asking this question, and that is to identify an intermediate. Oh, come on. Oh, my pen. Sometimes these pens dry out a little bit too quickly. Okay, let's identify. Intermediate. Alright, so now we talked about what a catalyst is and how we can identify it. Intermediates, they appear first as a product. We can't control how much intermediate is there, like we can a catalyst. The catalyst we have added as the experimentalist. But an intermediate is inherent to the chemical process, to the reaction mechanism that it undergoes. So, this IO- intermediate that is created as a product in an earlier step in a mechanism, and then in a later step it reacts with something else and it is transformed into other products. So, just like a catalyst, we were able to cross it out on both sides. Same with an intermediate, cross it out on both sides, but for a different reason. Because it's first created as a product, and then later it's a reactant, and disappears that way. So, our intermediate in this case is IO- ion. Okay. Now going back to this catalyst here, homogeneous or heterogeneous. So if you've learned about the different types of catalysts, homogeneous is something we see in solution. So right here we have aqueous hydrogen peroxide, and iodide is soluble in water, and so we then get a homogeneous mixture of the hydrogen peroxide and the iodide, and then the products, the water. Although the the oxygen gas is going to bubble away. It's a different phase. It's in the gas phase. Okay, but that iodide, that's aqueous, along with our hydrogen peroxide solution. Okay, now what about a rate law? A rate law, we write to start out, the rate law must be consistent with the slow step. So we're going to start out and we're going to make sure that we're writing it in the correct form of a rate law, which is rate equals, and then you've got your rate constants and whatever species are there that affect, whose concentrations affect the rate. So the rate law needs to be consistent. So we're going to make a note of that. Okay, must be consistent with the slow step. And we already figured out what the slow step is, right? So while you cannot write a rate law directly from the overall reaction, you can never, ever, ever assume it comes directly from the overall reaction. So we can't say rate is equals K times H2O2 squared. No, cannot do that. However, we can write mini rate laws for each elementary step based directly on the reactants in an elementary step. So we can do that for step 1, the slow step. Because remember, the rate law must be consistent with the slow step. Then we can double check and make sure that that rate law is written in essentially a way that is allowed, or in other words, follows the rules of rate laws. Okay, so let's just do our first step here. We are going to write a rate law, the form that it should take, and we are going to say, hey, this is step 1, and this has a rate constant we can call K1, a mini rate constant that goes with our elementary step. So let's just call that K1, the rate constant for the slow step. And because we're writing it directly from the slow step, we can write it as rate equals rate constant times the two reactants in this elementary step, that is the slow step. So we're following the acceptable form for a rate law from the slow elementary step. Okay. Then we are going to double check that this is in an acceptable form. And what I mean by that is that, do we have reactants, products, and or these are the things that are allowed in a rate law. And we look at what's here. We have hydrogen peroxide. That's a reactant. That checks out. That is allowed to be in a rate law. Iodide. That's a catalyst. That is allowed to be in a rate law. So, yes. And we're going to remind ourselves that intermediates are not allowed. And it works out here in a rate law. It works out for us here because there are no intermediates that appear in a rate law. So this form is absolutely acceptable, and it is a perfectly legitimate answer for a rate law. Don't worry that there's a 1 there that corresponds to the rate constant for step 1, because that rate constant ends up being the rate constant that is the overall rate constant. And that is because rate laws must be consistent with our slow step. It totally works out. Okay. Sometimes, just to give you a heads up, a warning, that when you write the rate law from the slow step, it is possible that sometimes you will have an intermediate appear. In which case, you need to do some little bit of algebra, some mathematics, and knowing what to do when that happens. And I did make a video about the steady state approximation and how you can solve idiots in them and some other situations like that. But this, we were lucky in this case. We got to write out the rate law directly from the slow step, and it checks out. Alright, well, I hope this was helpful for you. This is a real life exam question. So let me know if there are other kinds of kinetics problems that might be helpful for you, or really any other kind of chemistry problems. I am here for you. So let me know, and as always, thank you for the comments and the questions and just everything you do to connect and communicate. I love it. So thank you. And I will see you again next time.